Hello friends, in today's session we will learn about binding energy of a nucleus. In the earlier class we learned the term mass defect, right? Suppose we take Z number of protons and N number of neutrons individually and weigh them. Then it will have a total mass. But if we combine all these nucleons, Z number of protons and N number of neutrons into nucleus, its mass will be slightly lesser. That means when Z number of protons and N number of neutrons combine to form a nucleus, some mass is getting lost. We call that term as mass defect, called as delta N. And from the Einstein's equation E equal to mc square, we know mass can be converted into energy and vice versa. Energy can be converted into mass and mass can be converted into energy. If m amount of mass is converted into energy, mc square is the energy that we get from it. So here we can see when nucleons combine to form a nucleus, here a number of neutrons and proton, a number of nucleons are there initially and they combine to form the nucleus. Some mass is lost equal to mass defect, which is delta M. And that lost mass will be converted into energy obviously. So I can write delta E equal to delta M, which is the lost mass here, into C square. So if delta M is the mass lost when a nucleus is formed, then the energy liberated or the energy formed will be a delta M into C square, which is equal to delta E. So this energy is called binding energy. So we know if we weigh nucleons separately, then it will weigh higher, and if we weigh the same nucleons combined together in the nucleus, the weight is a little less, and that mass difference we can see between nucleons and the combined nucleus is called mass defect, and its equivalent energy is called binding energy. So this binding energy is what binds the nucleons together in a nucleus. We know all the protons are positively charged and neutrons are neutral, and there should be some energy to bind these nucleons together in a nucleus. So the binding energy provided by this mass defect is what actually holds the nucleons together in a nucleus. The magnitude of the binding energy will determine the stability of the nucleus. That means if the binding energy is large, then the nucleus will be very stable. So if we want to break down the nucleus into its component nucleons, then we should supply the nucleus with binding energy. So when the nucleons combine to form nucleus, the mass is lost and binding energy is liberated, and vice versa. If we need to separate the nucleus into its component nucleons, we should supply it with binding energy. Then we can separate the nucleus into its component nucleons. And for the nucleons, they will have a greater mass than the nucleus. And that difference in mass is called mass defect, delta N. And the corresponding energy is the binding energy. The energy corresponding to the mass defect is the binding energy. Delta M into C square will give you the binding energy. And another concept that you need to be thorough with is that if binding energy is large, the nucleus is stable. We have already told, we already went through that. And if a nucleus is having an amount of binding energy, then it is called the stable state or the ground state. So the ground state is the lowest possible energy of the nucleus. So if we supply the nucleus with some additional energy, then it is called excited state. So for a ground state, the equivalent energy is the binding energy, It is actually a negative kind of energy because we need to supply binding energy to liberate nucleons. So if we add some more energy, E greater than a minimum amount of energy, if we supply this energy into the nucleus, then the nucleus will become excited. It will be in the excited state. And finally, if we supply enough amount of energy to liberate all the nucleons, then the net energy possessed by the nucleons will be E equal to 0. That means we have liberated all the nucleons by providing amount of binding energy. And in that case, the nucleus will dissociate into constituent nucleons. Then the nucleus will not exist at all. Just the nucleons separated will be existing. So this is the concept of binding energy. Now let us formulate an equation for binding energy. Suppose there was Z number of protons initially, each having mp mass. Suppose there are n number of neutrons initially, each neutron having mn mass. Then what is the total mass we need to have? It is Z times mp plus n times mn. This is the total mass that we expect if we combine these nucleons. But when we form the nucleus, the mass measured will be m, which is lesser than this mass. So the difference between these two mass, the expected mass Zmp plus Nmn minus the actual mass that we measure m, this difference is called mass defect. So this is the mass defect delta m. Here you can see the first term in the bracket. This term indicates the expected mass if we combine Z protons and N neutrons, and this is the actual mass of the nucleus. And we know the binding energy equation for binding energy is delta E equal to delta M into C square. So it will be equal to Z mp plus N mn minus m into C square. So this will be the equation for binding energy. So in the coming session, we will learn more about binding energy and problems related to it. As of now, I hope that the portion is clear to you. Thank you.